Welcome. I'm Glenn Cochran. Join me for the story about New York's elementary science standards and how transitioning and implementing them will provide all our students the best science education. I have made a four-part series of programs with an opportunity to engage you in sense-making individually or in small groups. In the first part, we will look at this innovation of science teaching from the classroom perspective. In other videos, we'll review the K-12 coherence and structure of these standards and the impact on curriculum, instruction, and assessment. In the first session, we're going to consider how elementary NGSS instruction looks from the classroom perspective. As teachers transition their classroom into the New York State Science Learning Standards, they will notice a fundamental shift in pedagogy and the expectation for students to learn science as scientists and engineers figuring out and solving problems. You may have heard the science standards are called Next Generation Science Standards, NGSS. Actually, the New York version of NGSS is NSLS. Let's begin with some of your memories of science class. Pause the video and write or share a few of your science class memories. Maybe you remember trying to memorize terms and concepts that you didn't care about, or long lectures and hard books to read. When I think about my best science class memories, it's about a love of learning about nature, field trips, fun labs, and connections to teachers and friends. It's the intention of the NGSS style standards to bring the wonder and joy to learning science. NSLS informs three components of the system of student learning: curriculum, instruction, and assessment. I'm excited that now we have grade level guidance for the PK to 5 coherent science foundation for our students. This early science foundation will set the stage for our students in middle and high school. If we do our best with the transition and implementation of NSLS, students will be excited about science, and that should increase opportunity for learning in other subjects. Let's look at some of the innovations of NSLS. The goal is for students to make sense of phenomena by building on prior experience and applying an engineer's view to solving problems. Students will use the science practices as scientists do to figure out things about our natural world. A three-dimensional approach helps make science accessible to all students. It is not about students recalling facts and details. It's about constructing deep understandings of the core ideas of science. Do we need to memorize as much as past generations? Properly used technology that's in our hands today has reduced the need for much of that memorization. So what is phenomena? It is the engage in the unit or in lesson. It's not just a hook, but what we are looking for students to explain. Some characteristics is the phenomena must be observable to the students. It should be culturally relevant. It should engage and motivate students to actually figure out rather than passively learn about. And it does not always have to be flashy or unexpected. Three-dimensional learning. Students use the science practices or skills to learn science content through the vision of cross-cutting concepts. The coherence of the K-12 progressions is a design based on age-appropriate vertical alignment in 4 stages: K2, 3-5, middle school, and high school. And this also includes an alignment with the New York Next Generation ELA and math standards. So what are the most significant differences?
The framework was a document prepared by a committee of the National Academy, and we were asked to provide a vision for science education, and that vision is the underpinning of NGSS. The vision is that science learning has 3 dimensions, and those 3 dimensions are the science and engineering practices, what scientists and engineers do, and that students should do those things. The cross-cutting concepts, which are core ideas that scientists use as lenses for looking at problems, and which we usually have not taught, but which are very useful if you're asking students to solve problems for themselves. And finally, the core ideas of each discipline, building across the years of elementary, middle, and secondary school to provide a basis for any future science learning. If I take a very traditional classroom, the teacher talks. If the teacher asks questions, it's because they want the right answer. And there's very little of the students interacting with one another. If I go to a hands-on inquiry-based science classroom, there may be more student-to-student interaction, but it's mostly around doing something and not around the ideas. The idea of 3-dimensional learning is that research shows that learning by doing and by applying your knowledge to problem solving as you learn it provides a very different kind of knowledge than knowledge learnt passively. So we talk about teaching and learning and assessment as if they're 3 separate things. If they're done in an integrated way, for the student, it's all about the learning, right? And they're not seeing the assessment as just something I have to do to get a grade, but seeing it as an integral part of learning, and it's interesting.
This diagram shows that the math, ELA, and science practices, or what students are doing to learn, overlap. They complement each other. And when you look at the 3 intersections, building a strong base of knowledge through text, reading, writing, and its speaking grounded in evidence, construct viable arguments and critique reasoning of others, and engage in argument from evidence are all about what we want students to be doing. So how does this look in a 4th grade class? Let me tell you about the school before we go to the class activity. This is a school from Beaverton, Oregon. 58% of the students qualify for free or reduced lunch. 32% are ELL students with 29 different home languages. 19% of the students qualify for special education services. While watching this video, look for what students are doing, the use of language, student discourse, and inclusion. What does the teacher do to support instruction? If participating in a group, you might split the focus of the observations into student action, teacher action, and the use of language and equity.
Let's review the rules when we are having a science discussion. What are some of our agreements?
We know when to talk when nobody else is talking.
What about if you notice that somebody isn't sharing?
You can work together
to try to share and solve your problem. You bring them into the party.
You bring them into the science party, into the science discussion, exactly. The one thing that we worked on last week was where we had our Legos. What do those Legos represent?
Legos represent building on each other's ideas.
Okay, so remember today as we start getting into our science discussion here that we're building on each other's ideas. So what we learned about and what we've talked about the past couple of days is what might increase the rate of erosion. This was a model for a river, and when we increased the angle a little bit, can somebody explain what the water flow was like?
The water kept going faster, like when it was 10 degrees, it took 4 seconds, but when it was 55 degrees, it took 1 second.
The erosion forced it to go faster.
So that's a great place to start our claim. We think that increasing the angle of the stream table will increase the rate of erosion.
It left us with a lot of canyons plus the delta, which made it pretty interesting.
Let's see if we can see Christian's group up on the screen to see the rate of erosion with theirs. So we're looking for that increased rate of erosion. I mean, look at that. What is that even in 20 seconds? In 12 seconds it went through. Okay. How do we think this connects to our phenomenon and the mysterious landscape? My name's Jennifer Witten and I teach 4th grade at Beaver Acres Elementary. And what you saw today was the end of about a 2 or 3 week unit where our class has been working on a phenomenon. Started the unit showing them some pictures of a landscape in eastern Washington. It didn't explain how the land was formed. So what the students did after watching that was they created their own model of what their thinking was about how this landscape was formed.
This project is about discovering what created those weird holes. When we did our experiment, maybe, do you remember when the water started falling? It made a hole in the sand? Maybe it made a huge hole on the sand and made those black holes.
Oh my god! It's creating the delta. Oh, there's another one. I think there was a little hole and the water started coming in, and then it created more cracks because the water was coming in. And it created more holes and more, and it created bigger, which created a canyon, and that relates to our stream table.
Those holes are from those rocks, and then the water moved those rocks to a different area, and then made multiple.
What do you think, Kashmir?
I go with Nicholas's idea.
Experiment 1, which most represents the landform.
I think it would be experiment number 3, because number 3 added more water, and it was like more efficient. Maybe there was more water than less water. We pulled up the old video to see which one was more efficient, and I think it was number 3 because there was like a little delta and the whole thing almost collapsed.
This process started with watching a video of the landscape in eastern Oregon. And Mrs. Witten asked us what caused it, and what we thought was the waterfall. And then we did a few experiments to figure out what caused the landscape, and now we are making a model of what we think happened.
I'm just gonna give groups about 1 more minute and then we're gonna have a board meeting. We're gonna meet and present our ideas, okay?
We used to think that a drought dried the ocean up and a volcano caused the soot and ash. Now we think that a flood caused the canyon and carried the boulders to random places, and the water pressure caused the holes. And the stream table experiment supports our idea because when the water hit the land, it made a canyon and caused erosion.
Any questions for this group?
Is there still a volcano in this or no?
No.
How did the bits of rocks make the ash?
The water chipped away bits of rock.
Today what you saw was this board meeting where they revised their thinking. They had to include all the ideas from the activities that we did, and tomorrow we will watch the entire video and they will be able to see if what their theory validates what really did scar this landscape. This is part of some practices that have come with the next generation science standards. What I've been most excited about with these standards is the role that language plays in science, and I find that these standards really align well with language development. As you saw today, the students have a lot of time to share their thinking, their reasoning, they're using evidence to support their thinking, and then they're explaining their ideas and changing their thinking. All of those are science practices, but they're improving their language through learning new content. And as you can see, it's really engaging. Students are 100% engaged, and they're really doing some incredible work in here, I think.
Pause the video, take some time to consider how this science lesson supports student learning. Is there evidence this instructional approach aligns with all standards, all students? Here are some of my observations about inclusion for all. I noticed that there were expectations and clear class norms, giving respect to all students. Student discourse in group work, technology, recording observations, using ELA literacy support techniques, multiple methods express student thinking, modeling, ordering, phenomena-based instruction, more than a hook. The goal is for students to make sense of that phenomenon. Student-centered, teachers facilitating. Did you notice others? Let's take a look at what the students were doing and what were the teachers doing. These are some of my observations. The students were engaged, exploring, modeling, communicating, using technology, experimenting, using evidence, making claims, mathematical thinking, explaining, joining the party, inclusiveness for all students, arguing from evidence. And the teacher set the stage with the phenomena, facilitating groups, encouraging, supporting with ELA, teacher talk, not telling, setting the groups, providing ideas for experimentation, asking for evidence. So how does this compare to what we would see in a traditional class? In a traditional setting, the scientists and teachers have knowledge of science disciplines and pass that along to some students. In the contemporary model, all students make sense of phenomena in science, design solutions to problems in engineering, and students are acting as scientists and engineers. So the other three sections that we're going to be doing, this is the list of structure and components of NSLIS, transitioning the curriculum, and then assessments using NSLIS. So I thank you for participating. And join me on part 2 session, the structure and components of NSLIS. I hope this was helpful.